In this video, we will be discussing point estimators. When analyzing a population, it is rare that you are able to survey the entire population. Normally, you survey samples of the population that are representative of the entire dataset. Point estimators are values that can be seen as reasonable estimates for a population parameter. And point estimators are often calculated from the sample data, not the entire population. Some population parameters have a standard formula for calculating unbiased point estimators. For example, calculating a point estimator for the proportion parameter in a binomially distributed dataset, the point estimator p hat is equal to x over n, where x is the number of successes in the sample and n is the number of observations in the sample. P hat is used to estimate the true proportion of success outcomes in the dataset as a whole. This is an inherently unbiased point estimator of the true proportion p. Another population parameter that has a fixed calculation for an unbiased estimator is the variance, sigma squared. The sample variance, sigma squared hat, can be calculated using the formula seen here as a function of the sample observations, x sub I, and the number n of observations. Again, this formula calculates an unbiased estimate of the sample variance no matter what data set you're fitting it to. 1, 2, 3. However, when looking for the point estimator of the mean of a population, finding an unbiased estimator becomes slightly more difficult. There is no unique unbiased formula for a point estimator of the mean of a population. That doesn't say that there aren't any formulas to calculate unbiased point estimators of the mean. Of course there are, but the formulas differ as the population distribution does. In some cases, there will be more than one way to calculate an unbiased estimator for the population mean. In this case, you should calculate the possible unbiased estimators and then choose the one with the least variance. This is called the minimum variance unbiased estimator, or MVUE, of theta. You can check the variance of the estimators by either calculating out the variances or plotting the probability density functions of the estimators on a graph like the one shown here. In this case, the blue curve has the smallest variance and would be preferable to the other estimators shown. B indicates a more accurate point estimator because the spread is so compact. When working with point estimators, you will sometimes need to find the standard error, which is the standard deviation of the point estimator itself. This is denoted by sigma hat sub theta hat, or little s sub theta hat. However, this can be a fairly difficult quantity to calculate, depending on the point estimator in question. If the point estimator is the proportion of successes in a binomially distributed dataset, the standard error is quite simple. It's s sub theta hat is equal to the square root of p times q over n. However, the calculations get more complicated when the point estimators are biased or more complicated than a population proportion parameter. This is where we can use a method of sampling called bootstrapping, or the bootstrap method. This method makes it much easier to calculate the point estimators of a population and their standard errors. It is primarily computer intensive as it uses repeated sampling with replacement. Bootstrapping technique takes a large sample from a population, shown here in red, and then takes multiple smaller samples from that large sample with replacement. And each of the smaller samples, also called bootstrap samples, are used to calculate a point estimator for the population. And when you're finished calculating the point estimators for each bootstrap sample, you can average those to get a better point estimator for the population. And you can also calculate the sample standard deviation of those point estimators, which is now the standard error. So let's look at an example. Here, we'll generate a set of 20 data points that are representative of a larger population. For this example, we're going to assume a normal distribution, so we'll use the rnorm function to generate our data. And this function takes three inputs. First, the number of data points, 20, then the mean of those data points, and the standard deviation, which we'll call 2. And you can see that this command has generated a string or a vector of numbers, of 20 numbers, with a mean of 11 and a standard deviation of 2 that are from a normal distribution. We'll print those out here. There they are. And so now we're going to sort them. And for that, we'll just put them back in the same vector, only using the sort function. And using this function, they will be in ascending order. So now if we print them out again, same data points, but in a different order. So using this subset of data, we'd like to find a point estimator for the true mean value of the whole population. There are several ways we can calculate the point estimator for the mean. In fact, there are 4 ways to calculate the point estimator for the mean here. The first is a very simple calculation of the average of the data points. Sum them all and divide by n, which in this case is 20, or we can use the mean function in R, which does the same thing. And if we print this out, we can see that the mean of this sample is 10.37, which with a standard deviation of 2 is pretty close to 11. So now we'll move on to the second point estimator. And this one takes the middle 2 values from the sample and averages the 2, which is why sorting the data is so important in this case. So we'll do that like so. You specify the 10th data point and the 11th data point. Sum those and divide by 2. And that gives us 10.38, which you can see is pretty close to our average, our sample average, excuse me, which is a good indication that the data is consistent. It's not skewed in any one direction. So the third point estimator averages the 2 end values, the highest and the lowest value from the data set. So we'll do that in a similar manner using the first data point and the 20th data point, and then divide those by 2 again and get 10.75, which is a little bit different, but not completely. Again, the standard deviation of this data is 2, so it's not outside the realm of possibilities. Lastly, we can calculate the 10% trimmed mean. This calculation discards the smallest and largest 10% of the sample, and then recalculates the average. Note that the term 10% trimmed mean is slightly deceptive, as you're trimming 10% off both sides for a total of 20% of the data being removed. Because our sample has 20 data points, we will remove the 2 lowest data points and the 2 highest data points. Or, alternately, we can use the trimmed mean function. So we'll call this variable the trimmed mean. And again, it's the same function, and we input the data, only this time we're going to use the trim option, as you can see right here. And we'll use a 0.01. It takes this in decimal form. So now we can print this variable out and see that the trim mean is 10.26. So now that we have our 4 point estimators, we can see that they're fairly close to each other in value. No single point estimator is outside of 1 standard deviation away from the proposed true mean of 11, which is good. Indicates a truly random and non-biased sample. So now the question is, which estimator is best? The closest to the true mean value, the least biased. The rule of thumb here is that when the population distribution is normal, the sample mean x bar, our first point estimator here, 10.37, is the most accurate, followed by the trimmed mean. So more information on this topic can be found in your textbook, Probability and Statistics for Engineering and the Sciences, the 8th edition by J. DeVore.